Pluto is a far-off and strange diminutive planet, which was once an individual member of our nearby planet group's planetary family. However, ongoing alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this frigid world is on a potential impact course with Neptune. But how is it that this could work out? Also, what might be the results of such an enormous occasion? Are we seeing an intriguing galactic peculiarity? Or is there something else to this looming vast crash? Join us as we investigate the possibilities of a Pluto-Neptune influence. Pluto, a former planet that was downgraded to a bantam planet somewhat due to its impossible-to-miss orbit, remains a subject of interest and study in the cosmic local area. According to ongoing predictions by leading scientists, Pluto's path is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm of a potential risky impact between these two planets that could be a colossal danger to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our planetary group. It requires a stunning 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even completed one full upset. However, the interest doesn't stop there. Pluto's path is marked by its exceptionally curved shape, deviating significantly from the near-round orbits of the major planets. What compels Pluto's orbit even more exceptional is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to other planets. This inclination and circular nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its convergence with Neptune's path. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we may expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to grasp its unique inclination. Unlike the other planets whose orbits lie mostly near the ecliptic plane, Pluto's path stood out with its steep inclination and circular shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about figuring out how three things in space like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all interact in a complex manner. The terms astlibration and scope libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is astlibration. With regards to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is somewhere around 90 degrees away from Neptune. This spatial separation is vital in keeping their paths from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an extra layer of safety from potential collisions. Another pivotal aspect in this scenario is the VZK oscillation, named after three scientists, Bond, Zippel, and F, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling affects how they move. For Pluto's case, the VZK oscillation helps us understand the reason why its path near the Sun is so unusual. Though Pluto's path seems erratic, this oscillation helps keep it moving smoothly indefinitely. The VZK oscillation shows that even if things in space seem wild and random at some points, rules keep everything in order. These parts help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or get thrown off kilter. This three-body problem helps in understanding how these components change based on the way these space objects pull on one another. Focusing on this helps us learn about Pluto, our planetary system, distant universes, and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually turbulent, with minor deviations in initial conditions leading to significant differences north of millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the disorder under control. Recent computer tests have helped us understand how the large planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This association helps keep Pluto's orbit steady. However, Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable. Saturn contributes significantly as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a stable path for a long time, even billions of years. So, it's like Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are essential when it comes to the universe for keeping the control and consistency of celestial bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater turmoil and unpredictability. Bodies like Pluto might actually crash into others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions of it possibly colliding with Neptune in the future, understanding its orbit is truly significant. This gives us a clearer picture of the planetary system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and investigation of these peculiarities to grasp our place in the universe better. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a great example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is vividly shown in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual encounters has been super helpful for scientists to understand how Pluto moves in space. These simulations use intricate mathematics to simulate how Pluto and other space objects like Neptune pull on each other. By adjusting small details in the simulations, astronomers can see how even small changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's path. Although it has things like azimuth and scope libration to keep it steady, its orbit can still be quite wild and unpredictable. If you start with just a little difference in where Pluto is or the speed that it's moving over many years, the paths it can take can end up looking really different. Yet, even with this tumult, Pluto's orbit remains stable for long periods, like billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it seems to be all over the place at first. Predicting celestial events, especially when it involves chaotic orbits like Pluto, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often laden with uncertainties. While mathematical simulation provides a robust means to understand and predict the future paths of celestial bodies, they also highlight the limitations in our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to incredibly different outcomes, making precise predictions a daunting task. Besides, the turbulent nature of celestial orbits like Pluto reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us that our knowledge about the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects, impacting the stability and trajectory of other bodies within the system. So why are major astrophysicists just now raising worries about a potential crash among Pluto and Neptune? Despite all these intricate forces trying to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing astronomy, offers a unique perspective on the mysteries of our nearby planet group, particularly the fascinating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown domains of space. Tyson's stance on Pluto's renaming is rooted in the ever-growing knowledge of our planetary system. He sees the renaming not as a downgrade but as a necessary adjustment to our evolving understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He sees the complexities of orbits, such as Pluto's, as an indication of how much there is still to discover in space. The intrigue of these mysteries, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planet group. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine how we interpret the universe. Michio Kaku, another prominent physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often eccentric forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with advanced visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to anticipate and understand potential significant events. He sees the interactions between celestial bodies as a crucial area of study, not only for academic interest but for practical implications. The potential collision between Pluto and Neptune, for example, isn't just a theoretical scenario but an indication of the dynamic and often tumultuous nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from the impact on how we understand the nearby planet group to the potential need for future space interventions. Kaku's perspective highlights the importance of being prepared for the unexpected in space. His work suggests that the more we grasp the forces at play, the better equipped we will be to navigate and possibly mitigate the effects of astronomical events. Both Tyson and Kaku's views converge on the idea that space is a realm of continual discovery and that our ongoing understanding, while significant, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now but predicting how they could change in the future. The potential crash scenario between Pluto and Neptune serves as a case study for the broader challenges and exciting opportunities in space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space embodied by Pluto's orbit are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for years to come, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational influences acting on them. Thus, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential disturbances in orbital dynamics mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they could pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable with our current understanding, it underscores the importance of ongoing research and observation in space science. Advances in technology, including more advanced telescopes and programmatic missions, will help astronomers refine their models and predictions, ensuring that we remain informed about the dynamic and ever-changing nature of our planetary system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential collision scenario, while highlighting the dynamic and complex interactions within our nearby planet group, ultimately reminds us of the vast and still mysterious realms in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe.